The next talk actually was supposed to be given by my advisor, Professor Emilio Frazzoli, and I. We would have shared the talk. But unfortunately, Emilio is traveling, is experiencing some congestion. What a good thing for for this workshop. It's a perfect topic, right? So I'm gonna give the talk myself, and Emilio will join as soon as he can to join in the discussion and the commentary. So usually I would have introduced the speaker. Now I'm introducing myself. I am Gioele Zardini. I am a PhD candidate at ETH Zurich, working at the Institute for Dynamic Systems and Control in Emilio Frazzoli's group. Something about me, well, I studied mechanical engineering in the bachelor's and master's with a focus on robotic systems and control. I spent some time abroad working in Singapore for Nutonomy, what is now called Motional, one of these big autonomous driving companies, where I worked a bit on the design of these vehicles. Then I spent some time abroad at Stanford, then at MIT, performing research for my PhD. And today I'm going to talk about work that has been done in our lab that falls under the umbrella of co-design and coordination of future mobility systems. So whatever I talk about today, you will find in my webpage, which is this one on the bottom right. So it's called gioele.science. I don't think you can see my mouse, probably, but oh yeah, you can. Okay, great. So it's there you will find details about all the papers. So what's the talk about today? Well, we already heard a lot of talks today about new technologies, and in particular these autonomous vehicles and mobility on demand concept. And today we are going to first look at some past research done in our group to understand the impacts of this technology, and then we are going to talk about how we got inspired by the findings from this analysis. To look for a bit of a more general theory governing these systems. So to start, it's nice to see historically how we moved from across different concepts of mobility, right? So in the beginning, the only criterion to have a car was that it was faster than a horse, right? It was mass produced. Then slowly the car became something more related to lifestyle and status, right? So car nowadays is a consumer product. And the outlook for the future is that autonomous vehicles or cars without a driver will be, so many people say that those will be cool for convenience, sustainability, and eventually also safety. Right, but many studies show that safety is not the only factor characterizing these kind of systems. All right, but all these advantages might come with some drawbacks. For instance, having zombie cars or these cars going around without a clear scope. And so, if we want to frame it more as a general question, what can we predict what the effects of autonomous mobility on demand will be on the transportation? This connects to many questions that we had in this series of talks. All right, and we like to talk about this comparing heaven and hell, right? For this technology, there is always the positive and the negative side. Now, on the positive side, one has estimated that in most of cities, 30% of the cars could be sufficient to provide mobility. And what will change dramatically once one implements autonomous mobility on demand strategies is that these fewer cars will be much more utilized and hence also substituted more often, and so the market will be affected in this way. On the other hand, it depends. So these advantages depend on how one actually uses the service, right? So nowadays cars are typically parked for most of the time, and the idea right now in the current situation is that whenever people need to travel, everybody needs to travel, right? So the cars are on the road at the same time, and so the fact that now with the autonomous vehicles, mobility might be more accessible, might increase travel demand, and might even make the already existing problems more heavier to sustain. On another note, there is this whole theory that says that first and last mile connectivity could improve the efficiency also of public transit systems, right? Because you often need some autonomous vehicle-like service to bring you from a rural area to a more connected area. And also there is the idea that public transit is great when it is utilized, but it's a waste of money whenever it's not, right? On the other hand, the fact that many people in the future might buy their own autonomous vehicle could be threatening these advantages. For instance, if we imagine in the future somebody buying an autonomous vehicle and using it to go to the city center to do shopping, and while the person is doing shopping, the vehicle should just wait and go around waiting for the customer to be finished. Well, that's not the best usage of our resources, right? So there is these two sides of the medal. And another note, we have done some studies that show that in the future, with the increase of urbanization, mobility services might be manpower limited, in the sense that for some cities, there is a statistics that says that 1 person over 7 would need to drive a vehicle for the mobility system to be sustainable. So in this sense, autonomous vehicles could help solving this issue. On the other hand, there is a lot of people saying, well, if we have autonomous vehicles, all taxi and bus drivers will be out of job, and also not everyone will be able to afford autonomous vehicles. So you see, there are always these two sides of the medal. And what we have done in our group in the past years has been developing some simulation tool that we call Amadeus, as the composer that orchestrates fleets of autonomous vehicles. And this is a tool that allows people to test different strategies. It is based on Maxim. One can pretty easily take a scenario, implement a new fleet manager, and look at different performance metrics, such as the service time or the cost of the fleet and so on. Right. So this is a big part of the work we did. And thanks to this work, we were able to study different problems. One among all is the one of ride hailing. So we wanted to understand or to answer the question, is ride hailing bad for congestion? Yes or no? And the answer is it depends, right? But if on one end there are data that show that ride hailing could increase congestion, there are also other studies confirmed by some simulations we performed in our group that show that when the autonomous mobility on demand penetration is high enough and the fleet coordination is implemented, one could reduce congestion, even if we have other vehicles, or commonly known as selfish private car drivers, in the system. Now, this is nice because it connects a bit to what Klaus was talking about in the first part of today's workshop. One observes an effect on ride sharing that when one implements ride sharing, the total number of miles driven increases with respect to the case in which you have private vehicles. But the real question is which miles are increasing. So not all miles are the same, right? For instance, we did some studies for Switzerland for certain regions, and the results were kind of surprising. Well, it was essentially, we were seeing that most of the times these ride-sharing services, of course implemented with various techniques, were not really used, right? So you can see in this plot that most of the trips were performed by one or two parties in the vehicle, and whenever the big sharing option would be effective, maybe one could think of a line service that could substitute it, right? On the other hand, we also performed some studies for rural areas, and here the interesting thing was that especially in Switzerland, some rural areas are served by mobility systems like a train or buses, and those are implemented in using the spirit we want to provide service to the population, right? But most of the times those services are quite empty and very expensive. So there we saw with some studies that one can provide the same service or even a better service with these on-demand vehicles. Now, all of this to say what? To say that these studies that we were able to perform in the past were kind of ad hoc studies or ad hoc analysis. On one end, leveraging first principle analysis, on the other end, leveraging complex simulations. But they were all looking at particular instances where we wanted to fix everything in the system, change some variables, and understand the impacts, right? Now, connecting to what we were discussing before with Jinhua, the mobility systems in general are very complex, right? You have a lot of interactions. Actually, here, this round table is a nice figure to summarize with some pictures the great diagram Jinhua had in his presentation, right? You have a lot of different parties going from automotive industries up to academics and tech developers. Each one has a particular action space and objectives, and they need somehow to sit down at this virtual table and take decisions together for the positive impacts on society. Now, from the perspective of thinking about these systems, one of the layers of the complexity of these problems is that the different stakeholders belong to different categories, and these different categories are characterized by different properties, right? So if you think about it, in the private sector, one cares about business models to welcome new demands, or how to actually react to the policies of rules that the government put in place, or in which technology should I invest? Should I now also go towards the autonomous vehicles, or should I buy some e-bikes and offer a service of e-bikes? And the tools typically they can use to do so is they typically have pricing strategies. They can design their service. They can optimize the composition of their fleets, and of course they can design new technologies. On the other hand, the public sector has higher goals, right? Technically, you want maybe to meet sustainability goals, or react to urbanization, or you want to actually understand how to invest your public money for the next maybe 50 years. So it's something much more long term. Or you might have more basic questions such as how to guarantee the quality of life, or how to actually handle private companies that exploit public resources, such as ride-hailing companies. And again, here the tools, as Jinhua was saying, are policies, regulations, pricing, and incentive systems. Now, all of this is working on a different level, at different levels. One can think about the first one being the city level. Here, for instance, there are some problems related to optimal infrastructure choices or coordination of different mobility systems. There is then the service level, which is more about a single service. If, for instance, one could think about all the problems related to implementing optimal deployment strategies for autonomous vehicles or for other services. Then there is the actual platform level. So how do I design the single vehicle or the single mobility service? And finally, one can even go deeper and think about the subsystem level, where you really want to allocate resources. And this talk will essentially make the point that there are two layers of complexity, let's say at least two. It is complicated. One is the fact that we have a large and interconnected system, and the other one is that we have a lot of agents, and the interests of these agents are often conflicting. So I'm going to show you some results for both of these areas. The first one being the large interconnected system. And I want to show you some approach that we developed, in which we employ some tools from applied category theory and the mathematical theory of co-design to come up with system design policies for this large system. So what is the problem here? Let's say we look at this problem from the perspective of a municipality or policymakers. And we want to answer simple questions related to an autonomous vehicle-enabled mobility system. Like how many vehicles should we put in our city? Or how do these vehicles really affect public transit systems? So how should the two be connected? How performant should these vehicles be? So is it any vehicle, any autonomous vehicle, or should I limit the speed? Should I guarantee a certain speed? And also, how should I invest on the public transit technology? And as we were talking about before with Jinhua, the problem here is that usually to solve this problem, people focus on different subparts of the problem. The different parts are not modular or compositional, so really they don't match. And also they require different fields, right? So already in this workshop, we have people from transportation science, people from autonomy, which is a big field as a whole, economics, policymaking, and so on. But the idea we have is, can we allow interfaces between these different problems via this approach we call co-design? And here, the idea is that we want this big system to provide a certain functionality. For now, set it to be the demand to be satisfied. And we want to do that while minimizing certain costs. Here, for simplicity, think about investments, the externalities you produce, and the service level of your system, which you can think, for instance, as average travel time. Now, going about the details of the technology we use, it's beyond the scope of this short talk. But what I want to show you is that with this technology, we are able to essentially model different problems as these blocks that you see in this diagram. And you can take essentially a big problem like the design of a mobility system and decompose it into smaller blocks. Now, each one of these blocks has particular modeling properties, namely the monotonicity, or which sounds like restricting, but it's something that applies to many fields. The monotonicity between some functionalities you want to be providing with respect to some cost you will have to pay. And so the idea is that here we were able to model this, an intermodal mobility system, which you can see here in a cartoonish picture. So here we are really modeling people that are able to take routes depending on their objective or demand, and go through different parts of the network, not having to stick to a particular mode of transport. They can switch, right? And now the question was, okay, let's take such a system. Let's see with respect to externalities, total cost, and performance of the system, what is the best combination of micromobility options, autonomous vehicle option, and public transit option. And the idea is that those blocks, or this skeleton, is a model for the system, but then the way you actually populate the different problems or the different blocks can be done ad hoc for the situation you're in. For instance, this block on the left here can be fed some mobility simulations or some optimization problems, or some first principle analysis from traffic flow diagram properties, for instance. It's really, let's say, flexible with respect to what you want to use. Now, I want to kind of make you interested in the thing, and then probably after the workshop we will discuss about that. The kind of things we can do is that we can abstract away this big interconnected diagram into such a block, which, provided some demand, tries to minimize these three resources. And the kind of solutions we get are plots of this form. Now, if you think about the 2D case, in which you want to characterize optimal solutions with respect to average travel time and total cost or total investments, if you take the city of Washington, D.C. and assume certain properties and certain data for the city, like the real demand and the real costs that one has for public transit and so on, you can characterize optimal solutions as lying in this on this Pareto front. Okay, so each point on this curve is an optimal solution, which is characterized by a certain number of autonomous vehicles with certain properties, like this one is has an achievable speed of 35 miles per hour, a certain number of electric scooters or e-scooters or e-bikes, all micromobility options, and a certain number of trains, with also the option to have combination of those. And now you see, first of all, for such a complex problem, you don't have a single solution. That's clear, right? We like to provide more of a actionable information to policymakers. And the second thing is that once you look at these diagrams, as Jinhua also before was saying, the upper level needs to use this kind of diagrams to take a decision, right? It's not really our goal as a scientist to take a decision, but we're able to provide these kind of figures. Now, I want to show you, going back to this picture, that this approach that we are using is very cool for its compositionality properties. Now, if I take the very same diagram I was showing you before, and now I zoom in into the model for autonomous vehicles, instead of assuming simply this is a feasibility relation between some properties of the vehicle and its costs, but really trying to model this vehicle with the very same modeling assumptions with its complexity. So the design of controllers or perception systems, or even the modeling of the computation needed, I can actually do that. And I can essentially, following a Matryoshka-like principle, I can go on and explode these models. And I can actually start taking decisions also about the kind of controller I'm using to control the vehicle, or the sensor I'm putting on it, or the kind of algorithms I'm using to manage the autonomy pipeline, right? And once this is done, I can actually start from a very similar perspective, and now not only know how many vehicles with which speed, but also I can also find for certain scenarios what is the best composition of sensors, computers, algorithms that characterize the autonomous vehicles. So all of this is possible because the mathematical theory of co-design we are developing has very nice complexity properties. So the complexity of the solution scales only linearly when the number of options you have. And this allows us to start thinking a bit more compositionally about these kind of problems. Now, the second part is also one very interesting part, which takes into account the fact that all the agents in this system have different interests. And so you need to model the strategic interactions among agents. Now, if you think about it, just taking these four small blocks characterizing agents, you have mobility providers, public transport agency, customers, and municipalities. It is much more complicated than that, but let's stick with this assumption. You see that depending on the kind of temporal scale, you will have different interaction patterns, right? For instance, on a daily basis, the mobility providers can decide about the pricing strategies or operational strategies. For instance, if you've ever been to Singapore and you saw you witness some of the tropical rains, you see that some dynamic pricing strategies for mobility services are implemented quasi close to instantaneously. On the other hand, you can model the same interactions on a monthly, yearly, and even longer scale, and you see that the kind of things change, right? One can even start modeling regulations such as taxes and incentives, or geographical restrictions, and so on. So how do we think about modeling these strategic interactions? Well, we started thinking about this in terms of game theory, in the sense that we essentially, if you think about it, we have some sort of sequential game in which a municipality or some authorities take some decisions, some mobility providers react to those decisions, and in the end, the customers or the citizens react to the decisions of the players before. Now, of course, in realistic settings in our lives, this is let's say, the sequence of players might be swapped, there might be loops, and this is very complicated, but this is a good starting point to think about this problem. And this connects also to what Dario was presenting earlier today. All right, so let's keep in mind this idea of sequence. Now, we model this as a game. This is a well-studied category of games, sequential games. And now let's assume that you want to consider a real city in which we have different of these stakeholders. Let's say we have a municipality that can decide the public transit prices, and also some details about these prices, such as the cutoff distance for the difference in price strategies. And then you also have some taxes that you can put on autonomous vehicles and empty autonomous vehicles. So these vehicles that are looking for customers. Then you have some mobility providers. Each one can choose the kind of vehicle they want to use, the particular properties of that, as well as the pricing strategy for their service. And now we assume that we have a population of customers, each one has a different value of time, and they want to minimize their cost, which is both given by the time the trip will actually last and the fare they will pay. And now let's take some real demand data with real costs for citizens, and also let's account for congestion effects, and let's see if there are equilibria in this game I just described. Now, the first good news is that for such a setting, you have a lot of equilibria. And this is what I'm depicting here is equilibria of the interacting mobility service providers. So here you see those equilibria are reported in three main metrics, which are the costs for the emissions, the cost for the customers, and the revenue that the actual providers are getting. Now, if you go backward, now it's turn of the municipality to look at what are the different equilibria depending on their directions. So here you can see that depending on the objective of the municipality, which is political matter sometimes, you can get a certain equilibrium on this plot. For instance, if a city is customers oriented and really want the service to perform the best, and to have zero or smallest possible cost, you will have a certain solution featuring the introduction of a number of autonomous vehicles, some that are operating with some prices, and so on. Now, if you have a revenue-oriented city instead, which is kind of a strange city, but let's say it exists, you will have another solution, and so on and so forth. Like you could think about a green city, and that will have another set of optimal solutions. The idea here is not to give you the optimal solutions, but we think about a tool to reason about the different equilibria. Now, given these equilibria, we can also analyze the more complex things, like which one are really the best equilibria, or what happens if we suddenly forget about a metric and we project those. And we can also essentially understand some other system metrics, such as the modal share of autonomous vehicles, or the spectrum of taxes that one has to implement to satisfy a certain performance. So this to say, this is a very rich framework that provides a lot of insights. Now, all of this is based on now I'm doing some advertising. All of this is based on a book and on a class that we are teaching called Applied Compositional Thinking for Engineers. I left here some QR code. Someday we will finish this work in progress book that is growing and growing and growing. So if you're interested, look into that. And as a takeaway, I showed you very briefly, so bear with me, but I showed you a new approach to collaborative computational compositional continuous design, which shows how it is possible to create interfaces between fields and scales. Now, if on one hand I agree with the discussion we had with Jinhua, with the fact that it's very difficult to find a framework that describes all of the whole problem in a single piece, I also think that these interfaces are really needed, and I believe that the approach we are providing here can be used in the future to do so. And now the question for the future, or the question I'm working on these days, is that now I kind of showed you these two different directions in a separate way, but actually what we are working on is essentially embedding these strategic interactions into the theory I showed you as first, to kind of do these two things together. So this is like the technological challenge I have so far. So I want to thank the collaborators that made these results possible, and I will post this on the webpage. We have some openings in our lab, so if you're interested about these topics, definitely apply. And I leave you here with some references regarding which I talked about today. Thank you, and now I will have to do perform the task of asking myself the questions, probably. I see Emilio is here as well. Do you want to add maybe a couple of comments, Emilio?
No, really, you did a wonderful job, and I just like to take this opportunity to apologize for being late. I just arrived at my destination. I was underestimating traffic. I arrived just a few minutes late and didn't have the chance to actually give the talk. But thank you, Gioele, for giving the talk in my place on my behalf, and also for organizing this great workshop. So that's all I
Thank you, Emilio.
Thank you.
Thank you. Thank you very much.